Hello. So in this video, there are five topics as you can see on the slide. Number one, ray diagrams for concave mirrors, convex mirrors, and then defects, which is a spherical aberration. Then properties of mirrors, curved mirrors, solve problems on total internal reflection, and then finally lenses. Let's move. As you can see in this slide, you have two types of mirrors. First one is concave and the other is convex. We know P is pole of the mirror. The other letter used for P is M. F is focal point or focus, and then C is center of curvature, simply center. So this is concave mirror, this looks like cave, and this is convex mirror, opposite. So see, concave mirror looks like cave. Okay. Internal part of the cave is two types of images. We have two types of images. Number one is real and the other is not real, virtual. Real image is seen on a screen, but virtual never on the screen, only inside the mirror. Virtual image is always seen inside the mirror. Real image is upside down, always inverted. Virtual, upright or erect. Real image is made by only concave mirrors, but virtual images are made by concave, convex and plane mirrors. Real image is front of the mirror, but virtual image is behind the mirror. There are four important rays in all the ray diagrams, in all the image formation. Out of these four, you can use any two. Okay, very important, very much used. So, number one ray coming parallel to principal axis. You can see this ray from the object coming parallel to the principal axis. Parallel to the principal axis. So this reflects through F. So if this ray reflects, it goes through the focus, through the focal point. See, you can see in this image. Number two important ray is the ray which is coming through F. You can see here in this diagram, ray number two is not there. Okay. Ray number three is ray coming through C. Okay, this ray, if you can see from coming from the object, it will, you can see it, this is in the line of C. So when it reflects back, it goes through the C, you can see. Okay, and then last important ray is a ray which is falling here at P or M. It goes back at the same angle as it falls. Here is the summary. You can see the ray 1 going parallel, reflecting through focus. Ray 2 coming through focus, reflecting parallel to principal axis. And then, as I said before, the ray which is falling on the P or M, it goes back at the same angle, so it follows the laws of reflection. This is for convex mirror, you can see here. Now, where is the image formed actually? Which place, which location image is formed? So image is formed when there are two or more reflected rays meet. The point, the place where two or more reflected rays meet. For example, in this case, you see many rays reflect and meet here at the point of eye. And this is a place of image. This is the place where image is formed. Now here is the table summary. Images made by concave mirror. When object is at infinity far, it means far. In this picture, you can't see the object because the object is at far. So the position of the image is at focus, you can see. The image is formed at focus. And this column shows the nature of image. The nature of image is real, inverted, and very, very small. Very, it's a point size, like a point. Now, number two, when the object is beyond C, you can see the object is nearby C. And then, as I said, the two important rays are used here. The first ray is parallel to the principal axis, coming through the focus, reflecting through the focus. Then the second ray coming through focus and reflecting parallel to the principal axis. So the two reflected rays, this is reflected ray number one, this is reflected ray number two, they meet this place and hence image is formed here. Small image you can see. So where is the image formed? Between C and F. The nature is real, inverted and diminished. Again small. Diminished, it means small. Now case number three, when the object is at C, so interestingly the image is formed at C. This is a special case we can say and easy to remember. Object at C, image at C. Size you can see equal to the object size. Now next one. Between F and C, object is between F and C. Don't think this is an object. This is an object. We are always we put the object as upright always. So you see the object is coming closer to the mirror in every case. As we go down from 1 2 3 4 5 6, you can see the object is moving towards the mirror. Case 1 object was infinity, case 2 object was near C, case 3 object was at C, case 4 object came towards F, it comes closer to F. Next case object is at F, and then the last case object is between F and mirror. So this is the table, okay. And now here if you can see at the object, when the object is at F, the image is at infinity, far away, extremely magnified. Sometimes this case is called, or at this case we call that image is not formed, but actually image is formed but far. And here the last case, When the object is between mirror and F, you see this is the image. And this is the very special case. Again, this is the only case when image is virtual. Virtual, not real. See here, real, 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 real. And here, virtual. And if it is virtual, it is erect, upright, see, and it is magnified also, and behind the mirror. So this is a special case in case of concave mirror. So as we come, we bring the object towards the mirror, image goes away from the mirror. You can see image in the first case, object infinity, image at F. Second case, object comes near the C, image goes beyond F. And then next, object comes at C, image goes at C, goes to C. And then object comes towards F, image goes beyond C. Object comes at F, image goes at infinity. So as you see here, the object is coming towards the mirror, image is going away from the mirror. And you notice this case and case 5 is opposite to each other. Did you notice this? Okay. So now here images by convex mirrors, very simple. 2-3 diagrams only we need to keep in our mind for convex mirrors. You see the because this convex mirror is a diverging mirror. The ray goes diverted away, and we need to make virtual ray here, backside of the mirror, behind the mirror. So, and you see the object is in the first picture, the object is here, and image is formed here, smaller. Now when you bring the object near the mirror, image is a little bigger than the previous. When it is closer, object is closer, image is bigger again. That's why you have seen uh, wherever the object coming closer to the mirror, in case of convex mirror, image is slightly bigger and bigger. And again here also the important rays are used. See the parallel to principal axis. This ray is parallel to principal axis and goes in such a way, reflects in such a way that if you bring it back, you know, it it appears to come from F. Okay, and same if you see the other ray which is coming towards the F, it after reflection it goes parallel to the principal axis. So the four important rays are very important in every ray diagram. Now here is mirror equation. Let's talk about some formula. And formula we have here two. One is mirror equation and other is simple relationship between focal length and radius. So F equals radius divided by 2, or if you find R will be equal to 2 times focal length. And now here is the mirror equation, simplified mirror equation, direct. Just use these three formulas. If you want focal length, this one. If you want object distance, this one. If you want image distance, this one. Be careful of the signs, plus or minus. Always take plus if it is in front of mirror and minus if it is behind the mirror. Here is an example. Find the position of the image for an object that is 20 centimeter from a curved mirror with a focal length of minus 30 centimeter. The question does not mention which type of mirror it has, concave or convex. Okay, I highlighted the important numbers, important words in the question. So find the position of the image. We need to find position of the image. So that's why xi we need to find. Then object that is 20 centimeter. So xo is 20 centimeter. And focal length minus 30 centimeters. So f equals minus 30 centimeters. So because f is negative here, it's a convex mirror. And we need xi, direct formula xi, f times xo divided by xo minus f. We put the values f minus 30 times 20 divided by 20 minus 30. You see minus minus becomes plus. By the calculator you can do, or is simple. It gives 600, and then 20 plus 30 50 gives you minus 12 centimeters. That's now there is some defect in spherical mirrors. One is called spherical aberration. What happens sometimes, the reflected rays don't meet at single point. In this picture you can see, but here no defects. Here is the defect. You can see all the reflected rays are not meeting at one point, only here at one point. So this defect is called spherical aberration. Now here is total internal reflection, which is the next topic. See, the name is very clear. Total internal reflection. It means the reflection is happening completely, totally. like like the normal reflection, the light falls on the mirror and comes back to the same medium. This is called total internal reflection. You see in these three pictures, the ray is going from some denser medium to lighter medium, rare medium, maybe from glass to air. Okay, so you see we increase the angle of incidence here, see, from theta I to theta C. What is happening? It moves along the boundary of the two mediums. See, it means the angle of reflection, angle of refraction is 90 degree. Think of the situation when you increase this angle of incidence more than critical angle. See, you can see this new angle is more than critical angle. Wow, this time this refracted ray doesn't come to the same medium, comes back to the same medium. This is called reflection. No more refraction here. So that this is the case of total internal reflection, TIR. It happens always when the angle of incidence is greater than critical angle. Second important thing, it always happen in the denser medium. Here is the formula for critical angle, theta c. Sine of theta c equals n2 divided by n1. N1 is the index of refraction of medium 1 and N2 is the index of refraction of medium 2. N1 is generally the denser medium. Now types of lenses. See, convex, concave. Convex, other name converging, because it refracts all the light rays at one point. It converges actually, making all rays at one point, bringing all rays in one point, whereas the diverging lens diverges all the rays which is passing through it. It is interesting to know that concave mirror and convex lens have similar properties, like the twins. Convex mirror and concave lens have similar properties. Images by convex lens, you can see all one, two, three, six cases, as you know, similar to mirror, as I said before, because they are similar. So see here, the object is at infinity, so image is formed at f2. Okay, when then object is bringing near. Only difference between the lens and mirror is lens has 2f, 2 c. The c here we call 2f. For mirror we call c, center of curvature. For lens we call 2f. For mirror we call f, focal point. Lens also focal point f. No difference. Here we have two focal points, two center of curvatures. Okay, so this is the difference. You can see this is when the object is at f, image is at infinity. Images by concave lenses. See, this is, as I said, it looks like it is similar to convex mirror. It diverges. See, it diverges. Okay, so image is formed on the same side. Same side. Yeah, this is also interesting point about concave lenses, that concave lenses make images in the same side of the objects. Thanks for watching.